Hello and welcome to the Unit 3 review video. This video will go through the Team Ziggurat sheet that you received in class. If you don't have it with you, you can download it on the Edmodo page and print it out to work along with the questions. Well, let's get started. Question number 1, a glass of cold water warms as it's left on the counter. Well, I think it's a wise idea to always start with phase energy. Because this is water, it will have 2 bars of phase energy. It's liquid. And when it's left on the counter, it's still going to be a liquid, and so it will end with 2 bars of phase energy. Now this water is starting cold, which means that it's going to have a low thermal energy, which would be represented by 1 bar here. And it's going to warm, but it's being left on the counter, so it's going to be room temperature at the end here. Now our energy bars are going from a total of 3 to 4, which means that energy is entering this system of water. And the amount of energy that's entering is 1 bar, because the bar that is gained is 1 bar of thermal energy. The phase energy stays the same, which means the particle arrangement stays the same. Number 2, fruit juice at 20 degrees Celsius is placed in the freezer and turns into popsicles at -8. Well, I start with the phase energy, and it's starting as fruit juice, which at 20 degrees Celsius will be a liquid, so those particles will be somewhat spaced out. But then it ends up as popsicles, which are a solid, so that would be lower phase energy. Then the 20 degrees Celsius is slightly colder than room temperature. Frankly, you could put 2 bars or 1 bar. It does not matter as long as you show the final, which is -8. And so that's going to be considered very low thermal energy, so we could put half a bar there. So now our energy is leaving the fruit juice here. And in thermal energy, we go from 1 to a half. Now remember, to be clear here, we show our half as a triangle. And then from phase energy, we go from 2 to 1, so we have 1.5 bars leaving the juice. And now this energy is leaving the fruit juice and going into the freezer. And then remember, if you put your hands on the back side of the freezer, it's going to feel warm. That's where all of that energy is going. Next, a cup of hot chocolate cools as it sits on a desk. Well, hot chocolate, as you know, is a liquid, so that will be 2 bars of phase energy. And if it's cooling down, it's still going to have the same phase energy. It's still a liquid. Well, starting out hot, not boiling, but just hot, so we'll put 3 bars of thermal energy. And it's going to cool down. If it's sitting on a desk, it will cool down to room temperature. And so that would be 2 energy bars there. So this will be our cocoa. I don't know if I spelled that right. But the energy here is leaving from 3 bars to 2 bars. So energy is leaving the hot cocoa, going into the room. You know, if you put your hand right above it, you feel that energy that's leaving. And so 1 bar of energy is leaving. Number 4, some of the water you spilled on your shirt evaporates. Well, if it's water that you spilled, that's going to start as a liquid. And then it's evaporating, so it's the phase energy is increasing all the way to a gas, so 4 bars of phase energy there. Now it's on your shirt, so we can assume that it's going to be room temperature here to start with. And when we have a phase change, the temperature doesn't ever change during a phase change. And since it's your shirt and your shirt's not getting hotter or colder, you will still be at room temperature here. So this is water. And energy is entering the water because we have low energy going to higher energy. So we have 2 bars of phase energy, which means the particles are going from a medium distance together to a far distance. Phase energy is increasing. Number 5 is a 2-part problem. It says a pan of water is heated to boiling and some of the water is boiled away. Do 2 separate energy bar charts for each stage. Well, both of these are going to involve water, and in both of them, energy is entering the water because it's sitting on a hot plate, or a stove. Well, now we just need to separate this out. The first part here is the water as a liquid, so we start here with liquid, heats up to boiling temperature, but it doesn't start boiling. So it's getting to 100 degrees, and then the energy is going to begin boiling it, turning into phase energy, or being stored as phase energy. So our thermal energy to begin with is at room temperature, 25 degrees Celsius. Then it heats up to boiling temperature, which is 100 degrees Celsius, so that's 4 bars of energy. Kind of ugly looking bar there. And so we start at 2 and go to 4, which means we have 2 bars of thermal energy entering here via heating, the particle moving. In the second problem here, we now have water that is at 100 degrees Celsius. It's a liquid, but now the energy coming from the hot plate is going to be stored as phase energy. That's because boiling water is 100 degrees is the hottest water can get. So the energy can no longer be stored as thermal energy, it's going to be stored as phase energy. So going from 2 bars of phase energy to 4 means that we have 2 bars of energy entering here as well. Also by heating, because we're still, the particle motion is what's causing the energy to increase. So part 1, the water starts at room temperature and goes to 100 degrees, still at a liquid though. In part 2, the water is a liquid and then turns into a gas. Number 6, water vapor in the room condenses, ooh, look at that vocab word, on a cold surface. So we're starting with water vapor, which means that it is a gas. Water vapor has particles that are very far apart, which means it has a high phase energy. And it's going to condense, which means go to a liquid. Let's look at this thermal energy now. It's in the room, which means that it's starting at room temperature. But there's a cold surface in this room, which is going to be considered 1 bar here. So now energy is exiting the water as it turns from a vapor into a liquid. And so from 2 bars of thermal energy to 1 bar, that means we have 1 bar here. And then from 4 bars to 2 bars is another 2. So we have 3 bars of energy exiting our water. All right, next part here are these heating and cooling curves. Let me just change my pen color here. Number 1 says that we know 3 storage accounts to understand the changes in chemistry. State their names and describe how energy is stored in these 3 different ways. Well, the first one we know is thermal energy, and thermal energy is dependent on the speed of particles. So if you have a lot of thermal energy, your particles will be moving fast. If you have little thermal energy, your particles will be moving slow. High thermal energy means something is hot. Low thermal energy means something is cold. Next is phase energy, which is dependent on the arrangement of particles. If the particles are close together, that's a low phase energy, which would be a solid. If the particles are far apart, that's a high phase energy, which would be a gas. One area of confusion here is that sometimes students connect thermal energy with phase energy. They think, oh, because it's a gas, it's going to be moving fast. Well, it's going to be moving far apart, but you can have very cold gases, which aren't necessarily moving fast. So thermal energy is all about the speed of the particles, and phase energy is just about the arrangement, how far apart they are from each other. And then the last one is chemical energy. And as you may have noticed in our last station, we didn't even talk or learn about chemical energy. It's just there on our energy bar charts for when we get to that. And the chemical energy is energy stored in bonds. Best example I have for this is that Fiber One bar I eat every morning. There's a lot of energy packed into it, and my body breaks down that energy to give me energy. And that would be chemical energy.